Hello guys, hope you are doing absolutely fine. So welcome back to another video. So far we have covered Introduction to Modeling, Linear Regression and Logistic Regression. In today's video we'll be covering Decision Tree. We will first discuss what are tree-based models, then we'll see how to build a regression tree, and then how to build a classification tree. After that we'll do a comparison between tree-based models and linear models. Then we'll discuss few ensemble methods such as bagging, random forest and boosting. So basically ensemble methods are a way to improve the performance of your model. And then once we are done with the theory, we will do assignments as usual. So we'll do 3 assignments, one on classification, one on regression, and one on the ensemble methods. Alright then, let's hop in and see what is decision tree. So the tree-based models involve stratifying or segmenting the predictor space into smaller regions. So as shown here, this involves segmenting the predictor space into a number of simple regions. For simplicity, we keep these regions rectangular. So tree-based methods are simple and useful for interpretation. They can be used for classification as well as regression. Here we have shown a sample tree with notations. So vertical lines here are called branches. Dots are nodes, which could be internal nodes or terminal nodes. Now let's see what are the steps involved in building a tree. We will first see the regression tree. In step 1, we first divide the predictor space into j distinct and non-overlapping regions as shown here. Now you may ask, how do we create these regions? So for creating these regions, we use recursive binary splitting. In recursive binary splitting, all the values are lined up and different split points are tried and tested using a cost function. So we split the predictor space, that is set of our variables x1, x2, etc. using a cut point that minimizes the below equation. Now as given in the equation here, y hat r1 is the mean response for the training observation in region 1 and y hat r2 is the mean response for the training observations in region 2 and so on. So we keep on splitting the predictor space into more regions until a stopping criteria is reached. Let's say the stopping criteria is that the region contains values no more than 5 observations or any other user defined criteria. So that is how splitting is done. Now once the split is created, in next step we use every observation that falls into the region Rj. We make the same prediction, which is simply the mean of all the response values for the training observations in Rj. So let me explain this with the help of an example. Suppose we have data of baseball players. We have their salaries, number of years that they have played, and number of hits that they have hit last year. So we will use this data to predict the salary of base players. So as you can see, salary is a dependent variable and we will predict the salary based on the hits and the number of years. Let's say after performing step 1, we created our first region which has a cut point at as 4.5 and has divided the data into 2 parts. That is AR greater than 4.5 and AR less than 4.5. Then we created another region similarly. Now the region is further divided based on the number of hits as shown here. So our tree will look something like this. First split is based on the variable years. The players who have played less than 4.5 years will get average salary of 11,000. And second split is based on the number of hits. So players who have hit less than 118 hits in last year will get 18,000 as an average salary. And the players who have hit more than 118 hits will get average salary as 24,000. Now these salaries are the average salaries of the respective regions. And any value falling in this region will be predicted to have these mean values. So that is how the tree is created. And then we use these trees to make the prediction. Now that we have built a tree by using the training data, so the next task is to check how will it perform on the test data. A complex tree built on training data may overfit. Recall overfit means high variance and low bias. Or a short tree may not yield good results, which means it will have low variance and high bias. So a better way to address this is to build a very large tree and then prune it to select the best subset tree. So for this purpose, we use a cost complexity non-negative parameter, which does the trade-off between subtree's complexity and its fit to training the data. So basically you can say that it is bias variance trade-off. Then apply cost complexity pruning to the large tree in order to obtain a sequence of best subtrees. Then we obtain subtrees as a function of alpha, so that as we increase alpha, it will penalize the subtree containing more nodes. Now you can just skip the math and understand the process. We will not be doing this manually anyways, and R will be taking care of all this, but I'm just giving you the background, how things are being worked in the background. After this, we'll use k-fold cross-validation to choose the best tree. Now k-fold cross-validation is a type of cross-validation, and like CV, it is used to select the best value or model. We will learn this in detail in a later video, but for now just understand that CV is used to select the best value or the best model. So that is how a regression tree is built. Now that we know how to build a regression tree, let's see how to build a classification tree. A classification tree is built in a similar way as a regression tree. So here to create regions and grow the tree, we use classification error rate instead of RSS. The formula for classification error rate is shown here. Here row head mk is the proportion of observation in the mth region which are from kth class. So if you subtract it from 1, you will get the proportion of observation which are in the mth region but do not belong to the kth class. Hence they are called as misclassified and will contribute to classification error rate. However, it turns out that classification error rate is not the best way for growing a tree. So in practice, two other measures are preferable for growing the tree. First is the Gini Index, and the formula for it is shown here. And then second is the cross entropy. Again, the formula is given here on the screen. Now a small value of Gini Index or cross entropy shows the node is pure and contains observations predominantly from the same class. So our goal while growing a tree is to minimize Gini Index or the cross entropy. So that is how we build a classification tree. Now the next question is, we have linear models as well as tree models. But how do we choose which one is best and which one is to be used? Well, the answer to this question is not black and white, and it totally depends on the problem at hand. So if the relationship between predictor and response is linear, then linear model is best suited. However, if it is not the case, then decision tree may outperform. Now the advantage of trees are that they are easy to interpret and explain. But this ease of interpretation comes at the cost of accuracy of predictions. So there are multiple factors that needs to be considered before choosing which type of model we are going to use. Now moving on to the next topic, that is bagging, random forest and boosting. So the tree that we have learned suffers a problem of high variance. That is, the training and test predictions would vary to a great degree. Hence we use bagging, random forest and boosting to address this problem and improve our prediction accuracy. These are part of ensemble modeling. Now ensemble modeling is a powerful way to improve the performance of your model. It is the art of combining diverse set of learners, that is individual models, together to improve on the stability and predictive power of the model. So we apply ensemble learning over and above the various models that we have built. But before we learn about these methods, we need to understand a concept called bootstrapping. Bootstrapping is a resampling method in which we take multiple samples using the same data with replacement and then generate B-training datasets. So instead of collecting different samples, we generate multiple samples from a single sample. This process is called as bootstrapping. Now bootstrapping is a generic method and it can be applied anywhere. Now the first concept is bagging. Bagging uses the concept of bootstrapping and it is also a generic approach applied over different techniques. So let's see how bagging works. First we will see for classification tree. So here we have our training data set. From it we will take bagged samples, say B1, B2 up to Bn. Now from these bagged samples, we'll create models as M1, M2 up to Mn. So once the models are ready, we will give all the models our test observations and make predictions as P1, P2 up to Pn. Then we'll take average vote across all the models to classify an observation to a particular class. And this will be our predicted class for that observation. So that is how we do bagging for classification tree. Now for regression tree, the process remains the same up to step 3. But here, instead of taking the average vote across all models to find our prediction, we will take the simple average to get the predicted value. And that is how bagging works for regression. Now moving on to the next part. So remember, we are using ensemble methods to reduce the bias, or in simple word, to improve the accuracy of our tree models. In bagging, we create multiple samples and find the predicted value. But we must also know how accurate this value is. So for this purpose, we use something called out-of-bag error. Let's say we have a training data with 100 observations. Now it is seen that on an average, each bag tree makes use of around 2/3 of the observations. The remaining 1/3 of the observation not used to fit a given bag tree are referred to as the out-of-bag observations. So these out-of-bag observations are fed to all the models which do not have these observations in their bootstrap sample. And then average vote if it is a classification problem, or simple mean if it is a regression problem is taken for each of the out-of-bag observations which are passed through different models as their prediction. Then we can compare this prediction with the actual observation and calculate the error. So for example, total 33 out-of-bag observations were there and we predicted 25 correctly. So out-of-bag error would be 1 minus 25 divided by 33. So that is how out-of-bag error is calculated. Next we have VIF, which is variable importance factor. Now VIF tells us which variable is important by using RSS for regression and Gini Index for classification. VIF is a score, and higher the score, then higher would be the importance of the variable. So that is how we assess the importance of the variable. Now there are certain issues with bagging as well. So predictions for bagged trees suffer from a problem of correlation. Now don't ask me how. Let's just assume that it is proven by some intelligent people already. So we will just take it as it is. So what we did in bagging, we averaged the prediction over a large number of trees. But this does not help us overcome the correlation issue, and also does not provide a substantial reduction in variance. Now what we can do is, we can increase the bootstrap sample size to address it to some extent. Or else we can use another method called random forest to address this problem of correlation. So instead of using all the predictors, what random forest does is, it uses k predictors out of the m predictors for building the tree. Then we repeatedly build trees by randomly selecting k predictors until we build n trees predefined by us. You can think of this as decorrelating the trees and reducing the variance of our prediction. So that is how random forest works. Now if k is equal to n, then random forest becomes bagging. Then the last technique is boosting. It also works similar to bagging. In boosting, the trees are grown sequentially. That means each tree is grown using the information from the previous tree. So it basically learns from the previous information, hence also called as converting a weak learner to a strong learner. Now boosting does not involve bootstrapping. Instead, each tree is fed as a modified version of the original dataset. Also, there are different types of boosting algorithms like AdaBoost, which is called adaptive boosting, gradient T boosting, XGBoost, etc. So there are pros and cons of each of these algorithms, but we will not go into the details of it. Let us just restrict ourselves to know the important details that are required to implement boosting. So there are basically three tuning parameters that should be our focus. First is the number of trees, that is B, which means how many trees we would want. Now unlike bagging and random forest, boosting can overfit if B is too large. Thus we use cross-validation to select B. Now we are seeing this term cross-validation over and over. Don't worry, we'll learn this in the later part of this module. We have a complete section dedicated to cross-validation. For now, just understand that it is used for selecting the best parameter or the best model. Then the second parameter is shrinkage parameter, that is denoted by lambda. This controls the rate at which boosting learns. It is a small positive number that ranges from 0.01 to 0.001. Now the choice of lambda depends on the problem. Small value may require large B for good performance and vice versa. Third parameter is the number of splits, that is denoted by D. It is also called as interaction depth. It controls the complexity of the boosted ensemble. Usually D is equal to 1 works well. Now these tuning parameters are something that you can learn over time. But there are certain basic directions that I have already explained here that can be used for selecting these parameters. So these were the three parameters that are required for us to implement boosting. So with this we have completed the theory part on decision tree. We started with the introduction to modeling, then we did linear and logistic regression, and now decision tree is completed. Believe me, these are some very powerful algorithms and will be very useful. This is some really fundamental knowledge, and I hope you guys are enjoying the course so far. And also, if you just open the book, you will realize that these topics are very vast and they run into many pages. So what I have tried to do is, I have tried to summarize everything and presented you in a concise and comprehensive manner. Now let's just see what we have covered in this section. We first discussed about tree-based models. Then we saw how we can build regression and classification tree. Then we did a brief comparison between tree models with our linear models. And then finally we learned three techniques, namely bagging, random forest, and boosting to improve our models. These are called ensemble modeling. Now it's time for the assignments. So let's see how we can implement this in R. We will build two models in R, one for classification and one for regression. And in the third assignment, we will cover the ensemble methods. So let's end the video here. I'll catch you up in the next video where we'll do classification tree. Until next time, see you.